Okay, what we're ultimately looking at here is surface integrals. I want to start out with a relatively simple surface. Now, this is going to describe an interesting surface, but it's a start, and then we're going to add the K component, and we'll get a surface, and there are plenty of ways that we can add a K component. Okay, so what is this though? Well, this is in the XY plane because you got an I component and a J component, right? And we know and should understand deeply that a circle of radius 1 is parameterized by this, and this just goes back to the circular definition of the sine and the cosine function. This is because sine and cosine are defined. Here's theta. X is cosine theta. Y is sine theta on a unit circle. It's the most fundamental thing you need to know about trigonometry. And you use it throughout. You used it, whether you knew it or not, in differential equations. You've used it throughout calculus courses up to this point. Okay. So this definition, unit circle definition of a sine and cosine function, X is the cosine, Y is the sine. So if you do cosine theta times I plus sine theta times J, you're going to get a point on the circle where the radial line makes angle theta with the x-axis. If you don't thoroughly understand that, say this back, take my statement, break it apart, Google unit circle, implications of the unit circle, etc. Circular definition of the trig functions. Make sure you understand this. Okay. So for u equals 1, you have the unit circle. It's by the definition of the trig functions, sine and cosine. Okay. Now, if u equals 2, your R of t restricted to u equals 2. Gives you 2 times this. So every vector from here to here is going to get doubled, and that's going to give you a circle of radius 2. And then you're going to have a circle of radius 3. And a circle of radius 4. So that this describes the circle of radius 4. If you let u take every possible value, you get a circle of every possible radius. And the union of those circles is a whole blame disk, right? And of course, if u equals 0, you get 0i plus 0j, which is the origin. So you got a disk without a hole in it or anything. Okay. You need to understand this to understand what then happens So I'm gonna just conserve words, just keep stuff together. The unit circle, definition of something, you just have to assume, you know. And now what do we get in 3 dimensions? We trace out this vector for the same values of U and V. We might just start with the question, what do we get for U equal 1? What do we get for U equal 2? What do we get for any value of U between 0 and 4? Okay. So what do we get? Well, we can get it directly from here. Now, if you translate it to rectangular coordinates and can see what you got there, that's okay too. It'll at least tell you what you have, but the parameterization is the key, and it's the parameterization we're going to have to use to do a lot of surfacing. Okay. Now, if the surface happens to be the surface of the graph of a function of x and y, is equals some function of x and y, then we can do something very akin to what we do with arc length. Instead of multiplying by the square root of 1 plus dy dt, we multiply by the square root of 1 plus fx squared plus fy squared, and that gives us our surfacing. But that's not going to work generally. And we'll see examples of that. Okay, so what do we get? So what do we get for U equals 1? U equals 1. We have cosine VI plus sine VJ. So in the plane, if V was 0, but it isn't, I mean, if U was 0, but it isn't, in the plane anyhow, we have the unit circle, but then we have VK. There's a unit circle in the XY plane. This UK, not VK. And it's raised a few units above the plane by the UK. So R takes us out to a point on the unit circle and then raises us up 1 unit. And in this case, U is 1, should just be plus K. So we'd say 1 unit. So it's a unit circle, but it's floating 1 unit above the plane, right? Now, same picture. For U equals 2, we get a circle. Radius 2. I'll say floating. Two units above the plane. When I say the plane, in this case, I mean the XY plane. Okay? So here we got the XY plane, the origin, got a circle of radius 1 down here, gets raised up 1 unit. Circle of radius 2 gets raised up 2 units. Circle of radius 3 is raised up 3 units. Circle of radius 4 is raised up 4 units. We get a cone. Okay? Now there are various methods we could use to get the surface area of the cone, but the method that's going to apply pretty universally when you can parameterize your surface with continuous functions or contractional functions. Is this? RU is just this. Okay. It's a vector in the direction of the cone, depending on what U and V are. Not a unit vector, because this much would be a unit vector, but then you got the 1 here. So it's a vector, actually magnitude square root of 2. It's going to be the square root of cosine squared V plus sine squared V plus 1, right? Cosine squared and sine squared make 1, so it's 1 plus 1, so it's a square root of 2. So I can say, just this isn't particularly important. RU equals square root of 2 in the direction of the origin points of a line through the origin line on the cone. If you want to do it in cylindrical coordinates, theta equals constant gives you a plane of angle at angle theta with the x-axis, okay? If you cut this cone with that plane, you get that line. You get that line at angle theta. Okay, so that's a side note. But it's worth having a geometric picture of this thing. RV is negative sine VI plus cosine VJ. And this is, and it's, sorry, you're going to have a U. U, okay. Now, this is a vector. It's going to be at every point. Okay. If you're on the circle floating here 1 unit high, then this vector is going to be tangent to that circle. Okay? Let's just say it's tangent to the circle. Um, I don't want to write out the whole equation. Tangent to the circle at height u. So you got the circle at whatever height. Okay, you got some circle in a plane parallel to the xy plane. And these vectors will all be tangent to the circle. So what you have now is this vector is always along a line. Okay, you've got your cone. You slice your cone with a vertical plane through the origin at some angle theta with the x-axis, and you've got a line there. That's the direction of your r vector at any point on that line. You slice the cone at any height u, and you've got a vector tangent to that circle. Okay, so those two vectors are going to make some angle. Are they orthogonal? Well, sure. They're orthogonal. Just do the dot product, you're going to get 0. Okay. You got a negative sign times a cosine times a sine adds up to 0. Use just a factor. NK doesn't have a component for RV. Okay. Now, magnitude of this vector is u. So this vector always has magnitude square root of 2. This vector always has magnitude u. Okay. Well, another thing is then the RU cross RV all of the surface. Not going to go into all the details to prove that, but you just think about it. You got a cone here. You got a point on the cone. It's on some circle. The tangent vector is like so, and the RU vector is like so, and the RV vector is like so. So you've got this. You take the cross product, and it's tangent to the cone. Now you want to try to visualize that as best you can. Take a worthless piece of paper and roll it into the cone. Come on, roll. Got chalk on my hands. Making the paper slippery. Okay, not a great cone, but you see, you have this side here. The U vector at this point, let's say, grab it by the left hand and throw it fall apart, is like here. Okay. The RV vector is this way. Okay. If you do this vector cross this vector, I'm going to break my arm, but you're going to get a vector like this, outward normal. Okay. Now it feels like it's inside the cone, but it's outward for right-hand oriented cone. Again, I'm not going to belabor that point. We want to get the nuts and bolts of this process. Okay. So if we integrate, we'll go ahead and everything is magnitude of RU cross RV. And I'm just gonna state this, and we'll try to make sense of it, maybe a little later, maybe soon, we'll see. Magnitude of RU cross RV times DU dV. This magnitude of this vector multiplied by a delta U delta V gives you the area. Okay. I'll come back to this, but the total area is double integral to U dV. U goes from 0 to 4. V goes from 0 to 2 pi. Oh, parameterized surface. We can just do your surface is parameterized by a function by an R vector. You can just take the derivative R with respect to U, the derivative R with respect to V, take the cross product. And actually multiply for an integral over UV space. Okay. So we'll digest that a little bit. We might talk about that a little bit next time. That's a method. Now, why does that work? It's because the increments on that cone for given change in U and a change in V. Well, change in V changes the angle. Okay. A change in U changes the height. Okay. As in polar coordinates, the further you get from the origin, the bigger that change in angle, or the greater the influence of the change in the angle on the area increment. Okay, remember then polar coordinates, a delta theta comes out like this from the origin. The further you are out here to do an increment, the wider the increment is, the greater its area. So you want to go back to that. I don't want to redraw that. I mean, it wouldn't be easy to do that. We don't want to digress all the way back to that. We want to think about that. Basically, in this case, magnitude of RU cross RV is just square root of 2U. Very easy to calculate, but very easy to see if you just understand that RU and RV are perpendicular. In this case, it won't always be, depending on your parameterization and your surface. Since they're perpendicular, the magnitude of the cross product is the product of the magnitudes. It comes out pretty easily. Now, if you do the cross product, that's what you're going to find. Okay. That illustrates the process. Now the details differ, different surfaces. Okay. So digest that for a minute. And we'll look at a different surface. All right, I finally got this written down the way I wanted to. R is U cosine VI plus U sine VJ. V from 0 to 2 pi, U from 0 to 4, the same as what we have here, except now we're going to add, instead of just U, okay, we're going to add, I said 2 cosine V and 3 sine V. 2 U cosine V plus 3 U sine V. Okay, so what is this? Well, our region in the XY plane will still have our circles in the XY plane. Circles ranging from, well, the point at the origin on out to radius 4. Above each of these circles, though, we're not going to raise everything to height U circle, so we're not going to get circles up there. Okay, above this circle, we have some function. Okay, it stays above the circle, but maybe it goes up like this and then down like this. Maybe it's an ellipse up there. Okay, maybe it's a sine wave up there. Okay, could be just about anything. In this case, well, what's 2U cosine V plus 3U sine V? It's 2x plus 3y, isn't it? It's like z equals 2x plus 3y. And that's just a plane. So it's like we've got this cone, we've got a plane above the cone. Okay. Now, what does our method tell us? Without trying to visualize what everything means, surface area, which we'll use, that S looks a lot like the integral slide. Script does. Okay. Anyhow, that'll be an integral over my UV rectangle, because in UV space, this thing's a rectangle, and of course, shape. In terms of UV, it would be a color. Okay, so we go from 0 to 2 pi. We go to 4. Magnitude of RU cross RV. DU. Hope I wrote that down. Get it in the right order. No. Or is the inner, which is U. How do you do? Okay. Well, it's simple. We just do the cross product. So work it out. What do you get? Okay, now this is just mechanics. At this point, it's just kind of a mechanical process, although the more you think about the geometry of what the mechanical process is telling you, the better you understand what that is. So RU equals cosine VI plus sine VJ. Here might be out of the way. Plus this, okay? And RV equals negative U sine VI plus U cosine VJ. plus put a factor to U out here. And then it's times -2 sine B plus 3 cosine B. Okay, now that's, I have to read that, okay, but you should know what's there. Yeah, that's basically what you should have written out. Anybody see an error on that? Does that agree with what you got for the derivatives? Better. I'm gonna get worried about me. Okay, not worried about you. You're gonna be okay. Okay, there we got it. Okay, we gotta do that cross product. And it gets to be a mess, and then you gotta do the magnitude, which is an even bigger mess, okay? So you end up with something that might even be impossible to integrate. You're gonna have a radical with a bunch of this stuff in it, okay? But on the other hand, it might be that stuff matches up and simplifies to the point where that square root gives you something you can actually integrate, okay? But that's how you would do it. Now, we have all the machinery we need to calculate the flux, which is a big thing, or to calculate a mass. Okay. So I'm going to go back to this example, which is algebraically much simpler than all this stuff. Demonstrate. How you would find the mass. So let's say that you have a density function, rho of x, y, z. Where of course x equals find the right example here. I didn't write your parameterization here. So let's just write the parameterization. U equals R equals U sine V I plus U sine V J plus U K. Simple column. X equals U cosine V. Equal to my R U simply my R. Rho of X, Y, Z. You can then replace X, Y, and Z by U cosine V, U sine V, and U. Okay. Which gives you rho as a function of U and V. And to distinguish the rho of X, Y, Z from the rho of U, V, I'll put a rho sub P here. Make sure the P doesn't look like the rho, and the rho doesn't look like the P, which is the rho for our parameter parameterization. So rho P of UV would be square of U cosine V plus the square of U sine V, which turns out to be just U squared. Square them and back to the U squared out, you get cosine squared plus sine squared, gives you U squared. Chalk sniffing like the road starting to look like a P. Okay. I'll say rho P of UV times your area increment. And what's your area increment? Didn't use that notation before. Your rho of UV is U squared. Your area increment in UV space is magnitude of RU cross RP times your DU dV. Okay. Now, I'm not taking this down to the level of partitions and making a bunch of connections because at this point of the semester, with every pressure you're under and stuff, you're going to do fine. Just get the method down. Okay. You do want to understand something about the methods, you can think more deeply about it. I recommend you do. Right now, you're probably surviving. Nothing. Okay. Now, again, that's just then the square root of 2u. dA is just this, which, as we saw before, is just square root of 2u du dv. So you end up with just a square root of 2u cubed. Okay. Integrate with respect to u, you get a square root of 2 over 4. Okay. 1/8 square root of 2, whatever. Evaluate it 0 to 4, and then as your dv goes from 0 to 2 pi, you get a 2 pi. It's an easy integral. Unlike the integral you get that other thing. So might or might not turn out to be easy. Okay. So you just multiply rho by area, density times area. That's 50 million because you've done the mass of a line, you know, use line intervals to find mass and stuff, and volume intervals, find volumes and moments of inertia and centers of mass and all that stuff. Okay. All right. Now, what if we want to have a vector field? Well, you get the flux through the surface. You have some area increment with a normal vector. increment of area delta A. So that you write your vector area increment dA equal m delta A I'll do this in a little detail, but it comes out to something really simple. Again, magnitude of RU cross RV is the area multiplier for du by dv or delta U by delta V increment. That's a two-dimensional increment. It's like delta X by delta Y increment in the plane. This is your area multiplier. That makes some kind of pseudo sense. Well, depending on how we've digested some things, hopefully it does. Okay. Then your unit normal is RU cross RV divided by the magnitude of RU cross. So what is the vector dA? It's the unit normal times your delta A. I've got dA here, but I think delta A is the area of the surface corresponding to a delta U by delta V increment in UV space. You got this. Okay, well, there's your delta A. So what's the vector delta A? It's your unit normal times the magnitude of RU cross RV delta U delta V. What's your unit normal? So here's your unit normal. What do you get now if you plug this expression into this? Okay, well, that's what happens. Well, then RU cross RV cancels out. Yeah, okay, I know what you meant. You mean magnitude of RU cross RV? Yeah. Okay, you knew that. Okay. Yeah, you plug this into here, what happens? Make sure that this is all it's not all on the screen. Okay, this is just kind of rewriting what we have here, but there it is. Your delta A is just your area multiplier times your area in UV space. your delta A vector, you multiply by the unit normal. Okay? And now you have a vector area increment that you can dot with your surface, with your vector function and get the flux contribution. Okay? The component of flux parallel to the normal vector. Okay? Now, what's this? What's n? Well, n we just saw there's your unit normal vector. Your RU cross RV is normal. Okay. And I haven't totally explained why. You just got to kind of accept that. If you want me to explain why, we have time, I'd be glad to. I'd love to explain it, but you know, it's more than I want to lay on. Okay. Okay, so n is RU cross RV divided by the magnitude of RU cross RV. There's unit normal. RU cross RV is normal, so this is a unit normal. And when I plug it in here, the RU cross RV here cancels this, and you end up with okay. No, what am I going to write? These, okay. This is still built. This is okay. I get confused by this world here. Okay. Okay. So what are we going to do now? Flux of S through the surface, script S, is the integral of F dot dA over our region in UV plane. That's the simplest expression of the integral, but of course, you're going to want to write it as a double integral since we're doing an area of a region in UV plane. So be the double integral, in this case, from 0 to 4 and 0 to 2 pi of one more thing here. dA is the limit as delta U delta V approach 0 of delta U delta V, so it's RU cross RV du dV. F dot RU cross RV du dV. If you understand what these things mean, okay, this is a vector. Its magnitude is the area multiplier and its direction is normal. So kind of small. Magnitude is the area multiplier. Direction is the normal to the surface script S. And I'm using script S for the surface and for the area of the surface, which is a little ambiguous. Hopefully that won't be confusing. Okay. Well, that's pretty simple. Okay. Now, I haven't calculated RU cross RV. We're back to, this surface is RU cross RV. Well, again, I'm not going to write out the determinant. I'm going to say, I component cross I component gives you 0. I component cross the J component gives you multiple K. It's going to be cosine squared V times U. Then, so I'll use the room I have here. Distributing this through here. Sine V, J, well, J cross J is 0, but J cross I is negative K. But we're going to have then a negative sine V times U times negative sine V, which is going to be plus U sine squared V K. And then we're going to have I and J components because we multiply K by I, we multiply K by J. Specifically, K cross I. Here's K, here's I, positive J. Okay, so we're going to have negative U sine V I. And then K cross J is negative I. So we're going to have the negative of U cosine V. Okay. Now, sort them into IJK order. There's your RU cross RV. F, I haven't given you a specific function, right? So let's just say I don't want F to be radial because this thing is a cone and the sides of the cone come out radially from the origin, right? Okay, so I could let F be xi plus yj plus zk, but at every point F would be perpendicular to the normal. Okay, so you get 0. So I'll just say this, you can play around with it if you want. If so, if F equals U cosine VI plus U sine VJ plus UK, which is what you get if you plug in the parameterizations of X, Y, and Z, because X equals U cosine V, Y equals U sine V, and Z equals U, right? integral will be 0. So time blocks if f equals yi plus xj, and for good measure plus k, because I think that might end up to come out something a little too simple. Okay. Okay, first. Flux is the integral 0 to 2 pi, 0 to 4. But anyhow, you know, same thing we've got here. And that's right. And you read the form. Okay. The flux is an integral 0 to 2 pi, 0 to 4 of this same thing I wrote here. There's a dot there, the dot was perfect. Equals I'm gonna have to write it up here. F is going to be and I'm writing this, should be sine b here, this function, cosine b for this function. It's not plus uk, it's just plus k, dotted with our ru cross rb, which is negative u sine bi minus u cosine bk plus uk du dv. Now, why is it uk? It's, you know, two components of k, factor out the u, you got a sine squared plus cosine squared, that's just going to give you 1, you're just going to get uk. That should be pretty familiar too. Okay, well. Okay, we're dotting this, so it's u sine v dot negative u sine v. So your I components are going to give you minus u squared sine squared v. Here, you're going to get u squared cosine squared v. And it's minus. Okay, of course, you got u cosine v dotted with negative u cosine v. And that's going to give you u squared. And then a dotted with uk is plus u. Right, plus u down here. And that's with the du dv. And that's really easy to integrate. Okay. Okay, 0 to 2 pi, 0 to 4, U squared plus U, du dv. 0 to 2 pi. Then U cubed over 3 plus U squared over 2, evaluated 0 to 4 dv. And from 0 to 4, you're going to get 64 thirds and 16 halves, which is 128 sixths. What's 128 halves? I don't want to do that in my head. Sixty-four thirds plus 8. And you can directly approximate that. That's going to be 8. That's going to be 21 and a third. So 29 and a third. It's 59 pi. About 59 pi. Okay. Anyhow, you get enough, right? Now, the point is, not that hard. Just got to practice. Okay. Now, the hard thing is coming up with good parameterizations for surfaces. Most of the problems WebAssign has chosen, and I've gone with WebAssign's choices, so as not to be too unreasonable. You're pretty much given the parameterizations, or they're easy to find. Okay. Nothing too difficult. I did some stretches this morning in front of an azalea bush, and I was thinking about the surface integrals you would get with density functions to get the mass of one of those petals. Okay, and how you'd parameterize that. You'd have to use some approximations. Anyhow, I don't think you get a good closed pell function.